Have you ever wondered why two welds made with the same material can have completely different strength, toughness, and quality? The secret lies in something every welder and engineer must understand: heat input. Get it wrong, and your weld might crack, warp, or fail. Get it right, and you create a joint built to last a lifetime. So, what exactly is heat input? In simple terms, heat input is the amount of thermal energy introduced into the base metal per unit length of weld. Think of it as how much heat energy is deposited for every millimeter or inch you weld. The formula involves three key variables: voltage, measured in volts, current, measured in amperes, and travel speed, measured in millimeter. The result is given in kilojoules. Now let's understand the heat input formula. Heat input, or HI, is calculated using voltage, current, and travel speed. The formula is heat input equals voltage multiplied by current multiplied by 60 divided by travel speed multiplied by 1000. The result is expressed in kilojoules. Let's take a quick example. If voltage is 25 volts, current is 200 amperes, and travel speed is 300 millimeters. Heat input equals 1.0 kilojoules. That's how much thermal energy is going into the weld for every millimeter you travel. Now here's the real question: why does heat input matter so much? When heat is introduced into metal, it changes the microstructure of the heat-affected zone, or HAZ. This is the region of base metal surrounding the weld that doesn't melt but is significantly altered by the heat. The size and properties of the HAZ are directly controlled by heat input. Too low heat input, and you risk lack of fusion, porosity, and cold cracking, especially in high-strength steels. Too high heat input, and you get excessive grain growth in the HAZ, reduced toughness, distortion, and hot cracking. The sweet spot, the optimum heat input, gives you a well-fused, strong, and tough weld. One important detail most beginners miss: not all the electrical energy actually goes into the weld. Each welding process has a thermal efficiency factor, also called the arc efficiency factor. Here's something very important: thermal efficiency is not the same for every welding process. For example, GTAW, or TIG welding, has an efficiency of about 0.6. That means only 60% of the electrical energy actually goes into the weld. SMAW, FCAW, GMAW, and metal cord arc welding are typically around 0.8 or 80% efficiency. Submerged arc welding and plasma arc welding can reach up to 1.0, meaning nearly all the energy is effectively transferred into the joint. So when calculating heat input, you must multiply by the process efficiency factor. Because the machine may show one value, but the weld actually receives less. Let's talk about how heat input affects the mechanical properties of your weld, because this is where it gets really critical for engineering applications. As heat input increases, the toughness of the HAZ generally decreases. This is because higher heat input causes grain coarsening in the HAZ, and coarse-grained structures are more brittle. For applications in pressure vessels, offshore structures, or pipelines operating at low temperatures, this can be disastrous. High heat input also leads to greater thermal distortion. The metal expands and contracts unevenly, causing bending, warping, and residual stresses. In thin sheet metal fabrication, this is especially problematic. On the flip side, very low heat input on thick or hardenable steels, like chromoly, a high-strength low-alloy steel, can cause hydrogen-induced cold cracking, because the weld cools too fast and the hydrogen doesn't escape. So how do you control heat input on the job? You have three levers to pull. First, amperage. Increasing amperage increases heat input. Decreasing it reduces heat input. This is usually the first parameter welders adjust. Second, voltage. Higher voltage means a wider, flatter bead and more heat. Lower voltage concentrates the arc and reduces heat. Travel speed. This is the most powerful control. Faster travel speed dramatically reduces heat input. Slower speed increases it. Experienced welders instinctively adjust their travel speed to manage heat in real time. In professional welding, heat input is governed by the Weld Procedure Specification, or WPS. Standards like AWSD 1.1, ASME Section 9, and ENISO 15614 all require heat input to be tracked and controlled within qualified ranges. Deviating from the qualified heat input range means your weld procedure is no longer valid. Let's look at a real-world example. In pipeline welding, heat input control is absolutely critical. Pipelines carry oil, gas, and chemicals under pressure, often in extreme environments. Pipeline welding standards like AP 1104 require strict control of heat input to ensure the hose does not become brittle, especially in Arctic environments where temperatures can drop to -40 degrees Celsius. Welders must maintain consistent travel speed, amperage, and voltage to stay within the qualified procedure, all passes, all positions, all day long. Let's quickly recap what we've covered today. Heat input is not just a number in a formula, it's the invisible variable that determines whether your weld is a success or a failure. Master heat input control, and you've mastered the foundation of quality welding. If you found this video helpful, don't forget to like, subscribe, and hit the bell icon so you never miss our next video. Drop your questions in the comments below, we read every single one. See you in the next one.